All right, good day, folks. Thank you so much for joining us today at this webinar. We'll be starting in a few minutes. We're just waiting for folks in the lobby to join us. My name is Arya Shahar-Stambek. I'm lab scientist here at C-Therm Technologies. Thank you so much for joining us today. Just to let you know, this webinar will be recorded. And so if you have colleagues and other folks who wants to attend the webinar but they couldn't make it, please feel free to send the link to their way for the recorded webinar. And I think I'm gonna just continue with the webinar. It's been a few minutes past the time. So today's webinar will be in the theory and applications of very high frequency measurements of viscoelastic properties. This webinar is a joint webinar presented by Dr. Vincent St-Onge, research professional at University of Sherbrooke. Just a little bit of background about Dr. St-Onge. He received his bachelor's degree of science in chemistry, master's of science in materials chemistry, and a Ph.D. in polymer chemistry, all from University of Sherbrooke. And he's currently a materials characterization research coordinator at the University of Sherbrooke and a lecturer in chemistry, focusing on subjects such as polymers and characterization and electrochemistry. And so with his extensive experience in DMA and material characterization, and other viscoelastic properties, he's an expert in the field of material characterization. As I mentioned before, the majority of this webinar will be presented by Dr. St-Onge. And for folks who are new to C-Therm webinars, I'm going to give a very brief introduction. We are C-Therm technologists. We are focusing on thermal conductivity, instrumentation, and measurements using transient method, and obtaining values such as thermal conductivity, thermal effusivity, and diffusivity. And if you need your materials to be tested, or if you have any questions about this field, please feel free to reach out to us. You will be well looked after, and we'll be more than happy to answer any questions. But today's webinar will be more focused on DMA, as I mentioned. Just a little bit of brief introduction about C-Therm's product. This is Trident and core platform for measuring thermal conductivity. We offer 4 different transient methods for thermal conductivity measurements to be able to suit different needs for different applications and industries. And as I mentioned before, we are partnered with Metravib, and we have other partner in Japan, Rigaku Thermal Analysis. So we offer a full thermal analysis testing lab and testing services ranging from DMA, DSC, SDA, TMA, and DMA, and transient thermal conductivity measurements. So please feel free to reach out to us for any questions and any technical consultation. You'll be well looked after. So now we're going to continue with Metravib, our partner, and in France, and their DMA instrumentation and instrument series. So Metravib, with more than 50 years of experience in field of viscoelastic property measurements, has built really a great capacity for innovation and strong expertise in structure calculation, vibration, and physical measurements. And they offer testing services for a really wide range of applications, and starting from industries or for R&D or scientific research or any educational application. Which takes us to this slide, and this is Metravib DMA instrument range. Just starting from the left-hand side, you see the desktop series. So really here, the approach is a plug and run. So DMA 25 and 50 are capable of running all the classical DMA tests. For example, TG measurement, but with a great accuracy and with a wide range of frequencies, starting from very low frequencies up to 200 hertz. And really, you don't need, except of like electrical equipment and setup there, you don't need anything else, and the instrument will do the rest of the job with a software provided by Metravib, and you just need to plug it and start running the test. On the middle, we have DMA Plus series. So DMA Plus series are really the instruments that they are really they have a high capacity for DMA testing, and they are advanced DMA for viscoelastic property measurements. And these high performance instruments can be provided in 3 different models plus 300, which is a high force DMA providing 300 Newton force peak to peak, and 1,000 Newton force for plus 1,000 peak to peak, and as well as 2,000, which is 2,000 Newton force. And so as I mentioned before, really the plus series are unique in the capabilities that they offer, and for example, it's not only a DMA, it also offers fatigue testing with heat buildup module or crack growth testing, which is unique to Metravib DMA. And also we offer automated solution, which is expander and a robotic arm that runs a test, and it reduces the human errors, and it significantly increases the reproducibility of testing. And finally, the HF analyzer or high frequency analyzer, which will be the topic of today's webinar. And it's basically a high frequency testing. So if you're working across different industries, for example, aerospace or other application that you're dealing with vibration or any sort of high frequency deformation, VHF 104 is definitely a unique instrument for you because it can experimentally measure viscoelastic properties starting from 100 hertz all the way up to 10,000 hertz experimentally. There is no extrapolation. It measures all the properties experimentally with a direct measurement, and it's really unique, and that's the only instrument available in the market that offers that measurement without any calculation, such as time temperature superposition principles and building master curves. And you will be able to get direct measurement and direct test results at higher frequencies. If you're really interested in know more about our testing services and C-Therm and DMA testing, please feel free to reach out. We offer technical consultation and as well as demo testing. In the last slide, we just really want to show what our clients say and what our clients think about us. So I'm going to read a client testimonials for you here. We requested C-Therm conduct a technically complex test on our material. I was really impressed by how the report made it easy to clearly and quickly present the final result to our client. Thanks, C-Therm. So it was a comment on dynamic mechanical analysis testing here. We did here at C-Therm Technologies in-house with DMA plus 300 from Metravib. And I think I'll just pass it to Dr. St-Onge here. And thank you once again, everyone, for joining us. And Dr. St-Onge should be able to present now.
All right. Just let me make sure. Do you clearly see my screen now?
Yeah, we can see it, Vincent.
We can see it. Good. Thank you very much, Emma. Thank you also, Arya, for the introduction. So as mentioned today, I will be presenting a bit on the theory and applications of very high frequency measurements of viscoelastic properties using the Metravib VHF 104 instrument, which is the one you see in the picture here. We were lucky enough here at University of Sherbrooke to receive a large grant from the Canada Foundation for Innovation for the Polymer Big Data Interface project, which allowed us to purchase the instrument. And so my plan for today is going a little bit starting with the classical dynamic mechanical analysis to set the basis, and then move on to the VHF 104 and seeing how this instrument compares to classical DMA instruments. Then we're going to go a bit into more details about how it's actually working, how the analysis behaves, a few quick applications to wrap things up afterwards, and then the question and answers period afterwards. So let's start with the classical DMA section. So when we perform classical DMA analysis, basically what we're trying to measure is the viscoelastic response, which is labeled as M on this slide, of your materials. Basically, we will choose to apply either a stress or a strain and measure the opposite. And what we get is basically two different sine or cosine waves that have a phase element delta between the two, and they have different amplitudes. And from the amplitudes and this phase element, we can get the viscoelastic response. Now, very often, it's actually easier to represent this viscoelastic response as a complex number where we can actually separate the elastic component that we will label as a storage modulus from the viscous component of the viscoelasticity, which we will then label the loss modulus. And when we take the loss modulus and we divide it by the storage modulus, we get what we call the tan delta, which is the damping or the loss factor. And if you have access to the storage and the loss moduli, as well as the damping factor, then you have the viscoelastic behavior of your materials. And you can then get this values as a function of temperature or frequency to know the entire behavior of your materials. And just to give a general idea, in terms of the storage and the loss moduli, the typical range and what kind of materials are we talking about. So if you look in the very low range of moduli values, you're typically working with liquids. As you increase either the viscosity or the elastic component of your material, so you get the shampoo, gels, and hydrogels, you also increase the different moduli. Then you get to aerogels, liquid crystal elastomers, which are a bit special in their own categories. And as you keep increasing, then you reach to the elastomers and rubbers, which will be likely the main focus of the talk today. And if you keep increasing the moduli, then you have plastics, soft metals, and then thermosetting resins like epoxy resins. You get metals and then ceramics. So really the storage and the loss moduli clearly indicates basically how hard it is to deform your material, whereas the tan delta provides insight on the viscoelastic behavior of the material. So the ratio of viscous to elastic behavior. So if you have a low tan delta value, something that tends towards 0, we're going to be speaking of something that is a purely elastic solid. And as you keep increasing it, we go towards the purely viscous liquid. And just something more specifically about tan delta equals to 1, it's basically when you have a kind of a solid to liquid phase transition happening. So if you know your moduli and your tan delta, you know basically how your material is going to behave as a function of temperature and frequency. So this is the information that we're typically looking out for when we do DMA analysis. So when we're going to be running analysis with the VHF 10.4, this is also the kind of information we're going to want to obtain in the end. So just to compare quickly the VHF 10.4 with the classical DMA instruments, I'm going to start by assuming that most of the people attending the webinar have never seen the VHF 10.4, so I took the liberty of taking a quick video of the instrument we have here at the University of Sherbrooke. So when you open it, you then get this kind of little oven in the vibration damping chamber. Inside this oven that you see here is where your sample will be going. And so the sample will be screwed on top of this little part here, which is the shaker. And we're basically going to be shaking or vibrating this shaker at various frequencies, up to very high frequencies, to measure the properties of the material. So in terms of comparing the VHF 10.4 to a classical DMA, in terms of space that it takes in the lab, what you can see is if you compare to the high forces DMA that were presented a bit earlier by Aria, you see that in terms of space, it takes about the same lab space as the classical DMA would. In terms of a variety of deformation that you can apply, the VHF-10-4 is limited to really tension and compression, whereas the classical DMA would allow you to perform tension, compression, shear, three-point bending, or even single and dual cantilevers deformation type. So for sure, a classical DMA might seem to be more versatile, but there's a very good reason why the VHF-10-4 is also a very interesting instrument. Is that in terms of frequencies, it can reach up to 10,000 hertz. So maybe I haven't explained it earlier, but VHF stands for very high frequency. And the reason why I keep saying 10-4 is because it's 10 to the power 4, which is 10,000 hertz, which is the limit of what the instrument can give you. And so because it can reach up to 10,000 hertz in a single and direct measurement, it can reach up to much higher frequency than classical DMAs can. And so if you're interested in looking at the behavior of your materials at higher frequencies, you'd no longer have to use the TTS or time temperature superposition model using the WLF equation to mimic or to predict or expand the range of frequencies, which is extremely time consuming to do, because then you have to cool down your samples and you need to take at least like 5 different temperatures. So it takes a lot of time compared to a direct measurement. So typically a measurement on the VHF-10-4, like we've done here at University of Sherbrooke, they're going to last between 30 minutes to 1 hour. Whereas if you had to do with a classical DMA to reach up to 10,000 hertz, it would likely take you about 8 hours to perform. So there's a lot of time savings to be done with the VHF-10-4 if you're interested in high frequency measurements. That's actually the reason why we bought the instrument in the first place. You also have access to a temperature control on the instrument. So if you would like to span the frequency range, you can also perform the TTS model with the VHF-10-4. For sure, the temperature range is a bit more limited than what you get on a classical DMA, but it's still more than enough for most typical needs. And one of the limitation, I would say, of the VHF-10-4 is that it applies very well to rubbers and elastomers, but not necessarily as well to harder materials. So in that aspect, the classical DMA would be more versatile. So when choosing between a classical DMA or the VHF-10-4, it's really important to know exactly what it is that you need. So if you need to know the behavior of your samples up to 10,000 hertz, so very high frequencies, and you work with, I'd say, soft matter, and the VHF-10-4 is definitely for you. And one specificity is that the VHF-10-4 is actually designed to use vibrations and resonances of the material, whereas with classical DMA, you actually want to avoid that as much as possible, or else your instrument is going to shatter during your measurement. So this is a very important difference because it means that the VHF-10-4 will work very differently to extract the viscoelastic behavior of your material as what a classical DMA would do. So if we move on to how the instrument actually works, the first step in knowing how the instrument works is knowing how the sample is being prepared. So I've taken 2 little videos to show you how the sample assembly is being made, because it's very different from the classical DMA. If you look to the video on the left, you have access to a gluing toolkit. Basically here, the white part that you see is the part that we're going to be screwing to the shaker of the instrument. And everything else that you see at the moment is accessories simply to align where you're going to be gluing the sample. So here I'm handling a little rubber I think it's a silicone rubber sample that I was handling on that video. So you have to apply a thin layer of glue. Then you will glue the sample on the base of the sample assembly. Hold it in place for a few seconds to make sure that it sticks very well. It's a contact glue, so it sticks. It takes about 30 seconds for it to stick, and then about 5 to 10 minutes to dry completely. And then we repeat the process, because on the top of the sample, we will be placing a little mass on which we will be able to screw an accelerometer. So all this gluing tool is really only there for the alignment, to have something that is perfectly centered. And so when the gluing is done, the sample assembly that you get for the analysis resemble what you can also see on the right, on the video on the right. Once you have that, it's very, very important to apply a little bit of grease on all the components to avoid any cavities that would then induce additional vibrations on your measurement. And then when everything is greased all together, we will just have to screw things in place and put the accelerometer on the top. As you saw, the base is shaking, so literally it's a shaker. And that's actually the deformation that will happen during the measurement. It's going to shake up and down at various frequencies. And what we will actually be measuring is the acceleration from the accelerometer of the base and the acceleration from the accelerometer on the top of the sample, as you can see on this video. It's very important to make sure that the wires are not applying any form of stress on the sample, because it will also change a little bit the measurement. Then you can close the oven, and then we're good to go to run the measurement. So as I mentioned, what we are literally measuring with the instrument is what we call the acceleration transmissibility, which will be defined as the H function, which is the ratio of the acceleration of the head. So this would be the mass or the head of this the sample holder, divided by the acceleration of the shaker or the base of the sample. And then it will also give us the phase element as a DH value, which will be in degrees. So as we go, we'll start at low frequencies. If you take your sample at low frequencies and you start to shake it up and down, at low frequencies, the mass will respond pretty much the same way as the base or as the shaker is responding. So your accelerations or your acceleration curve from the shaker and the mass will be exactly the same. It will overlap perfectly, so there's no phase differences between the two curves. And they will also have very similar amplitude. That means that the H function will be around 1 when we start at low frequency. As we increase in frequencies, then we will reach the resonating frequency of the material. And at the resonating frequency of the material, both the acceleration wave of the shaker and of the mass will be perfectly out of phase with a minus 90 degrees phase difference. And the acceleration of the top or the mass, the top of the sample, would actually have a higher amplitude than the one of the shaker. As we can see here, it's slightly higher. That means that the H function will also be higher than 1. And as we keep increasing the frequency, the two curves will shift further apart. And then the amplitudes of the mass, the accelerometer on top of the mass, will actually be lower than the one from the shaker. And at some point, we'll reach a point where they are perfectly in opposite phase, minus 180 degrees, with an H function that is below 1. And what this actually means, this is the kind of graph that you should expect that is actually given by the instrument. So as we are at low frequency, your H function is about 1, and your phase angle is at 0 degree. As we increase, we reach the resonating frequency, so your H function increases, and then your phase element goes down to minus 90 degrees, and then further on. And this is exactly the kind of curve, or a typical curve, that you should expect to obtain from the instrument. Now, this instrument works based on the vibrations models. So knowing the frequency at which the vibration happens is actually something very important to extract the viscoelastic behavior of your sample. And there's a very simple model that allows us to tune or predict the position of the resonance frequency of your materials simply by knowing your material's Young's modulus, its sample area, the sample thickness, and the mass that we put on top. So the mass that you saw in the videos was an aluminum mass that weighed 4.7 gram. 5 gram, on which we add the 4.7 gram of the accelerometer. So a total of 9.7 gram. Sample area, well, you can define it by changing, either if you have a rubber, you can cut it different size. The thickness, same thing. The Young modulus, if you don't know it, you can probably guess an approximate value to help you predict which mass to take, because there's a series of different mass that you can put on top of your sample to shift or to tune the frequency to the resonance frequency that you need. So when you have this, you can predict where it's going to happen. And then you can also define two additional frequencies, which are very important, which is the lower limit of validity of the model and the upper limit. So the lower limit is given by dividing the resonant frequency by 2, and the upper limit is very often not anywhere close. It's very often higher than 10,000 hertz. So with the VHF 10.4, it's not a problem. We'll always have something good up to 10,000 hertz. But if you want to really go from 100 hertz to 10,000, that means you need to tune your resonant frequency to 200 hertz in order to have the lower limit to 100. So this is something that's very important to take into account, because if you have a frequency that is lower than the lowest limit, the wave is no longer resonating, it's actually propagating inside your sample. And that means that the model that will be used to extract the viscoelastic behavior will not be valid. So it will give you something, but it will not be meaningful. And when you have defined your range of validity, you do a little bit of modeling where you input in the software your H and the DH function with some modeling parameters that you can tune, and then it will output you the storage loss moduli, and as well as the tan delta curve. And so here the curve that I've drawn is something that would be typical if we were seeing the equivalent of a glass transition happening. But in your rubbers, if you go at high frequencies, you very likely don't want to see that, and you would actually expect to see like just a straight line all over the range of frequencies when you're testing. And when you have that, you know the behavior or the viscoelastic behavior of your material. So let's look into some applications of the VHF 10.4 that I've done in my lab. Let's start with a natural rubber that has been vulcanized with sulfur. So this is the kind of sample that we got. We were able to cut just a circle or cylinders from one of the holes here that had those parameters. So the thickness was about 1 centimeter thick. The surface is given here, 2 × 10⁻⁴ square meter. The Young's modulus of that rubber is about 1 10 to the power 8 Pascal. The mass that we put on top was the small one that we saw earlier in the videos. The thickness on centimeter. The density of the material here, we estimated it to be about 1,000 kilogram per cubic meter. We don't know the exact value because we haven't measured it. But if we use those parameters with the simple models that we saw earlier, we would expect to have the resonance frequency about 2,300 hertz, which would mean the lower limit about 1,150 hertz, and the upper limit at about 16,000 hertz, which is beyond the limit of what the instrument can give us anyway. But that's all good. When we ran the measurement, this is exactly what the software gave us. So here you see that we were supposed to be around 2,300. We're actually slightly under 2,000, so the model is not perfect. But it also helps, it still helps us to define approximately where the frequency or the resonant frequency was. And from that, when we did the modeling, we ended up getting the mechanical modulus of the sample as well as the tan delta curve, as you see here in blue. And it's perfectly in the range of what was expected. We see that over the valid range that we had, we can see a modulus that is nearly perfectly flat. And we see a tan delta curve, which is between 0.2 and 0.3, which is close to what was expected for the material. So it works quite well for a natural rubber. We also ran some analysis for an external client who provided us with a silicone rubber material. Again, we cut the material with this thickness, and it had this surface area. We used the smallest weight. We estimated the density of the material, again, about 1,000 kilogram per cubic meter. As you see here, the Young modulus was a bit lower than on the previous one, and by doing so, we expected to have the resonant frequency about 2,700 hertz, and the upper limit would be 45,000 hertz, again, very far from what the instrument can provide us, showing again that the upper limit is not the limiting factor. Here, it's really the lower and the resonance frequency. So we ran the analysis at different temperature to see how it would behave. And then you see that we always get the exact same curve. As we increase the temperature, the resonant frequency is shifting towards lower frequency, which is also something that is expected. And what you see now is that at the end, or at close to 10,000 hertz, you start to see some weird things happening. So even though the theoretical limit of this sample would have been 40-something thousand hertz, here, because we get to see some weird things happening, we actually are limited in terms of upper frequency. So this can be due to poor sample preparation, or sometimes the sample preparation is simply challenging because you have a soft material and you need to cut it and maintain a very uniform and very flat surfaces. So these are part of the challenges that you can face. You do your best, and this is the kind of curve you end up. So basically, we would limit the range of validity to about 6,000 hertz on this one. And then for the lower one, we take the resonance, which is about 3,000. So maybe 1,500 would be the limiting value. So if we take a valid range, this is what the curves looks like. We can see here on the phase curve that there is a little dip going on here. And so when we do the modeling for to get the viscoelastic properties of the material, we can see also this little dip happening at those frequencies, and it gives rise to a peak in the tan delta curve, which can be due to different effects or different things going on in the material. Without knowing the exact formulation, it's actually quite tricky to try and assess what it was, but the client was quite happy to see those peaks. So whatever they were to be expected. And so the VHF 10.4 was actually quite amazing here, because as you see, getting results up to 2000 Hertz in this case was barely impossible with classical DMAs. And here they were able to see it with the VHF tensor. We also use the instrument for teaching purposes. So we had the students in the lab replacing a typical polyacrylate 3D printing resins by a biosource, still a polyacrylate biosource this time, resin that would give something that would be labeled as a weak thermosetting resin. So the glass transition temperature would be higher than room temperature, but the sample would have relatively soft or weak mechanical properties. So again, this is the kind of sample that the student printed. So it's a layered sample, so layer by layer printing. So that means that the sample is far from being anisotropic. So there's a lot of anisotropy happening in there, which can also explain why we got maybe some weirder results than what was expected. So here, in terms of the resonating frequency, we would have expected 1,800, and we can see when we measure it that we're closer to 3,000. So there's a bit of a shift happening here with this thermoset, but we could still manage to do the measurement after a bit of tweaking on the mass that we added on top of it. And then we could extract the modulus, and the modulus was consistent with the Young modulus that we had measured by another method. And the tan delta at 0.1 is also something that is very consistent with a thermoset. So again, the VHF TEN4 was able to provide such a measurement much faster than just a classical DMA would have. And we were able to obtain those results for very different types of materials. Now, maybe one thing I would like to mention, apologize for going back, there's a reason why the VHF TEN4 is not necessarily suited for hard materials like thermosetting resins, is that very often you end up having a Young modulus of your material, which is very high, which will always shift your resonating frequencies towards very high frequencies. And so that makes it more challenging to obtain valid data because often you end up being over 10,000 Hertz for your resonance frequency. For sure, we can play on the thickness of the sample and on its size and also on the mass we put on top to try and shift the resonating frequency down to lower frequencies. But they still present quite a challenge to analyze with the instrument. So just to wrap things up, I hope you have learned a little bit more about what the VHF TEN4 can do for you. Keep in mind that the main reason why one would like to use this instrument is because it can give you a direct measurement up to 10,000 Hertz, saving you a lot of time in the lab. You can still change the temperature if that is something that you need, and it's a very good instrument that applies very well for rubbers and elastomers. We were able to do a weak thermoset with it. Doesn't work as well for very hard material, unfortunately. So just to finish things, I know C-Therm offers a good services in terms of thermal analysis. So I don't want to be stealing their clients, especially because they're offering me the chance to present the instrument today. But we also offer quite a lot of services, either in thermomechanical analysis, but also in different other aspects like chromatography or mass spectrometry. So if you go on this link, you'll be able to find most of the services that we offer. I think the link has been shared in the chat with you. Unfortunately, the website is only in French, but if you have any questions, please send me an email. I'll be more than happy to get back to you with hopefully good answers to your questions if you have. And if you have any questions for today, I'll be happy to do my best to answer them. Thank you very much.
Alrighty, thank you so much, Dr. St-Onge, for the informative presentation. As Dr. St-Onge mentioned, for folks who are interested in asking questions about the details of the VHF, please stick around. We'll have a Q&A session for you coming up. But just to wrap things up here, and just to walk you through an outro, if you're interested in learning more about material characterization with different methods, or if you want to enhance your knowledge, we do have an additional resource at C-Therm.com. It's a library of the webinars, blog posts that you can have access and take advantage of those knowledge and use them for your applications. And also feel free to follow us on LinkedIn and stay updated for the new services and the other news that we publish about thermal analysis and thermal conductivity measurements. The upcoming webinar schedule can be seen in the slide. We have upcoming webinar with Rigaku, our partner in Japan, titling Enhancing Pharma Processes with Preclinical Development and Pre-Formulation, April 16th. And another one, Material Characterization for Fruit Packaging and Cold Chain Storage, will be up April 17th. That's more that covers more like a broad range of characterization, starting from thermal conductivity, DSC, as well as DMA. And the last one, evaluating the thermal conductivity of nanoparticle enhanced fluids on April 29th. We'll also be at two different events: Thermal Management Expo, booth number 410. Please feel free to stop by and have a chat with us, as well as Material Characterization Showcase in Houston, Texas. We are always open to help our clients and asking all the questions, so please feel free to stop by. And I guess that will take us through the QA session. So the recording of the webinar will be stopped here, and Dr. St-Onge will be online here with us to answer